Welcome to this video with an example of analyzing determinate structures. This is one of several videos in a short course on equilibrium posted at terje.civil.ubc.ca, Toolbox, a website that contains notes, examples, and algorithms for structural analysis. The structure shown in this figure consists of a horizontal frame member and an inclined truss member. That means the truss member can only take axial force, while the frame member can take bending moment and shear force, in addition to axial force. We often interchange the words beam and frame member, including in this video. But formally, a beam member is primarily intended to carry bending moment and shear force, while the frame member carries axial force as well. Notice also the 10 kN per meter uniformly distributed load on the structure. The objective in this video is to determine the bending moment diagram and axial force diagram. Shear forces will also be considered. In the course on indeterminate structures, we will learn how to find the degree of static indeterminacy for a structure. It turns out that this structure is determinate, which means that equilibrium is all we need to reach our objectives. Physically, the fact that the structure is determinate means that any vertical displacement at point B due to shortening of the truss member will not affect the bending moment diagram and shear force diagram of the beam. This is a key characteristic of determinate structures. It is because of that fact that we can isolate the horizontal beam as shown in this figure. It is supported by a pin support on the left-hand side and by the truss member at point B. Not only that, we also recognize a cantilevered beam and also a simply supported beam, once that cantilever has been addressed. This point harks back to other videos in this short course on equilibrium. Notice here the bending moment diagram that is associated with the cantilevered beam subjected to uniformly distributed load. We know from previous videos that the bending moment at the base is QL squared over 2. That evaluates to 1.25 kN/meter. Notice also that once we have determined the bending moment value at key locations, in this case at point A and point B, then we simply draw a straight line in between as the bending moment diagram for that part. Next, we address the distributed load between A and B with the cantilever out of the way. This is a simply supported beam, with the well-known QL squared over 8 bending moment diagram shown here. The conclusion is that the final combined bending moment diagram for the full horizontal beam is as shown here. We know well how to establish the shear force diagram from the bending moment diagram, so we proceed to the axial forces. That is more interesting because it involves equilibrium at point B. The starting point for that is to determine the shear force for the beam ends coming into that joint. From the right-hand side comes the cantilevered beam, whose shear force is Q times L, which is a 5 kN clockwise shear force. The bending moment diagram for the beam on the left-hand side consists of two parts. One is a triangle with maximum value 1.25 kN/meter. That gives a constant shear force diagram with value 1.25 divided by the length of that beam segment, which is 1.5 meters. The other portion of the bending moment diagram for that beam is AQL squared over 8 parabola. The associated shear force is QL over 2, as shown here. The total shear force is 8.33 counterclockwise. When we transfer those shear forces from the members to the joints, then we see that both are pushing the joint downwards. The next slide considers equilibrium of that joint in order to determine the axial force in the inclined truss member. Notice that the total shear force of 13.33 kN is known, while the axial force in the truss as well as the horizontal beam is unknown. By following the three-step process that is now well known from the analysis of truss joints in this course, we first draw the known and unknown forces on the joint. Then we play around with the direction of the unknown forces in order to determine a closed force polygon. Finally, we use the direction of the arrows from that diagram to put the forces back onto the joint, recognizing which forces are in tension and which are in compression. It is exactly that result, shown on the right-hand side, that gives the axial force diagram shown below. The axial force in the truss member is in compression, that is, negative, because the force from the force polygon pushes on the joint. Similarly, the axial force in the beam is in tension, because the force arrow from the closed force polygon is pulling on the joint. Thanks for watching this video. Please visit terje.civil.ubc.ca Toolbox for more videos and more material relevant for the modern structural engineer. See you soon.